Hello everyone. The problem that we are gonna be solving today is permutation sequence. So let us first read the problem. The set 1, 2, 3 to n contains a total of n factorial unique paths. That means they're giving us something. They're giving us some information. By listing and labeling all of these permutations in order, we get the following sequence for n is equal to 3. This. So you can see that it is all in ascending order and all of it is string. All of it is string because the return type is string. Given n and k, return the kth permutation sequence. So for n is equal to 3, k is equal to 3, this is our answer. So let us just write it down. So for n is equal to 3, what does n is equal to 3 means? That in our pool of numbers, we have 1, we have 2, we have 3. In our pool of numbers, we have 1, 2 and 3. So this is basic math that to fill 3 spaces with 3 numbers, we have a total of n factorial ways. That means total unique combinations is nothing but n factorial. N factorial is nothing but 6. Now let us write that in ascending order. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2 and 3, 2, 1. So these are 6. Now what is the first thing that comes to your mind? How do you think about this problem? How did I think about this problem? So the first thing that came to my mind was to legit brute forces. That means just get all of the permutation sequences, sort it, and then return the third one, return the kth one, right? This is the very first thing that came to my mind, and it is the brute force solution because this will work. It is not that this will not work. How will this work? At every step we will have a pool, right? Because numbers cannot be repeated, right? So we have a pool of 1, 2, 3 right now, and we have a decision to make what one to choose as the first letter. So we can choose 1, we can choose 2, we can choose 3, right? We can choose from all these 3, and the pool that remains with us at each step is decreased by that particular number. So 1, 3 and 1, 2, this is our next pool. Now for each of these we go again. We have 1, 2 because we chose 2 as the second number, and here we chose 1, 3 because we chose 3 as the second number. Here our pool is this, here our pool is this. So now again here we just have 1, so it is 1, 2, 3, and here it is 1, 3, 2, and here our pool is empty. So whenever our pool becomes empty, we return, right? We return 1, 2, 3, we return 1, 2, 3, we return 1, 3, 2, we return 1, 2, 3 and 1, 3, 2, and then the same thing again return, right? So in short, we are saving this. Whenever our pool becomes empty, we are saving, we are keeping a track of all the permutations, right? So the same thing will happen for here as well and here as well, right? So this is how we get all of these permutations, and we store it in a data structure. We can store it in an array list, we can store it anywhere. So we can store it, and we have to sort it then, because let's say this is added before this, because we did this recursion first. We are doing this by recursion, by the way. So yeah, and we did this first, and we then have to sort this. And then after sorting, we return the kth permutation. Now this is a very inoptimal approach, because to calculate this via recursion, it is very expensive. Our time complexity would be n factorial times n. n factorial. So if my n is equal to 10, let's say this is very, very high, very high. I cannot afford this time complexity for larger numbers. I need something that is much smaller, right? So this is not an optimal approach. N factorial to count the number of ways, and n to save it. N to save it here via string builder, because since the return type is string, so we'll need to keep a track. We'll use a string builder essentially, and then when this is done, we add it into the data structure using string builder dot toString. Right? Simple Java. Right? So this costs n. So it's n factorial times n. So the time complexity for this brute force is n factorial times n, and this is our brute force. Now the optimal solution is a little observation based, right? It is a little observation based. So now if you observe here very carefully, you have buckets. You have starting with 2, starting with 1, starting with 2, starting with 3. You have groups, right? You have groups. This is a total of 6, right? This is a total of 6, and we have 3 numbers. We have 3 numbers. Our n was 3, our n factorial was 6. So we have a total of 6 divided by 3, 2 groups. We have 2 groups starting per number. Also, this can be proven mathematically. Because let's say you assume this to be a container where this is fixed. So the number of ways to fill this with a pool of 2 things is again n factorial. Here n is equal to 2, so it is 2. So this is 2 ways with 1 as constant, 2 ways with 2 as constant, and 2 ways with 3 as constant, right? But so now if you notice, let's say all of this is 0 indexed. Each permutation is 0 indexed. So here if you see, starting with 1 we have 0 to 1, starting with 2 we have 2 and 3 indexes. I'm talking about indexes, 2 to 3. Starting with 3 we have 4 to 6. Now we need to check where our k lies. Where does our k lie? Our k was 3. That means in index notation, my k is second index, right? Second index. That means essentially my k is equal to 2. Right? So where does k is equal to 2 lie? K is equal to 2 lies here. Right? So since it lies here in this range, it is but obvious that our first, so let's say we know that it lies there, right? So since we have 3 options, since it lies in the second part of it, we know that we need 2. Right? Because everything starting in the second group starts with 2, right? Now how do we go about these 2 places? So now if you see, our pool has been decreased. Our pool now is, instead of 1 2 3 was our pool. We know that this is fixed. So now our pool becomes 1 and 3. So now we treat this as a 2 problem, right? So the permutations here would be n factorial. N is 2. So we have 2 factorial permutations. That means 1 3 and 3 1. 1 3 and 3 1. Right? So now again this is all 0 indexed. So 0 to 0 lies here, 1 to 1 lies here, right? But now in this, right, in the next remaining part, that is this part, where because if you see here 2 are there, right? So which one is our combination? Which one is our combination. Essentially, the combination that we're looking for here is the first one. That means zeroth index for this one. We're looking for zeroth index of this one, right? So that is nothing but k dot group size, k mod group size, right? So what is our k? Our k was 2. What is our group size? Group size was 2, so 0. So this is our zeroth index. So since now our k becomes 0 for this part, our k becomes 0 for this part. Our k becomes 0 for this part. Now since our k is equal to 0, we know that the index that we are looking for is this. So we know that it belongs to this group, and this group has 1 as its starting. So we put down 1 here. Then we subtract this problem, again break down this problem into a single path where our pool is nothing but 3. And here again, when we apply the same logic, we have n factorial combinations, which is 1 factorial, which is 1 at 0th index, and our k is nothing but what was our k now? K was 0 mod group size. 0 mod group size is 1. It is 0. Again our k becomes 0 here, and basically we just select this, we add it down here, and then again we go down. Our pool is empty. So we know that this is our answer. So I hope this simple example was kind of clear on how we thought about this, right? So now let's just quickly code it up, right? Now first let us define a pool, because pool is something that we desperately want. List of integer. Pool is equal to new array list, and for int I is equal to 1, I is less than equal to n, I plus plus, pool dot add I, right? We're filling up the pool with integers 1 to I. Now essentially what did we need, right? What did we really need to calculate the group size? What was our group size? Our group size was nothing but n factorial divided by n every time, right? Because we're dividing. So essentially, how did this come? We're dividing 6, that is n factorial. We are dividing n factorial permutations by the number of items we have in the pool, right? So 6 divided by 3 was 2. Our group size was 2. So hence this is our formula for group size. So basically we need something to calculate the factorial. So we can either create a factorial function and run it again and again, but it is not really efficient. So we just make a simple factorial array wherein we plug in the index, that is, let's say if it is 1, so we get the value. Let's say we plug in factorial of 1, so we directly get 1. Let's say we plug in factorial of 2, we directly get factorial of 2. We get factorial of 3, we directly get factorial of 3. So essentially this is something that we want, right? So integer fact is equal to new int n plus 1. Why n plus 1? Because we need the n factorial also, right? And if I declare this as n, my array will stop at n minus 1, so I need to declare plus 1. So we declared this. Now we know that fact of 0 is equal to 1. We know that is a basic thing. Now for int I is equal to 1, I is less than equal to n, I plus plus, fact that I is equal to fact that I minus 1 times I. We are filling up. That's it. Now we decrease k is equal to k minus 1, because since we are using zero based indexing, k is equal to k minus 1. And now to store we use string builder. SB is equal to new string builder, and for int I is equal to n, I is greater than 0, I minus minus. So now we calculate int group size is nothing but fact of I divided by n. No, actually fact of I divided by I. Right? We need that. But if you see, what is this? This is, let's say my n was 3. So it is 3 into 2 into 1 divided by 3. So essentially it is nothing but factorial of n minus 1. Right? So instead of doing this, we can also do this. Right? So we get the group size. This is our group size, and we calculate the index. As k divided by group size. And we sp dot append pool dot get index. Right? So pool dot get index. So let's say my pool for n is equal to 3 was 1 2 3. For n is equal to 3, what was index? What was k? My k was given as 2, because it was 3, then we boiled it down to 2. So my k was 2 divided my group size was 2. My index became 1. So that means we took this, right? So that is what is happening here. So sp dot append pool dot get index, and then we remove it from the pool. Remove index. We remove that index, and then we go down to the next thing, k mod group size. We go down to the next iteration. And we just return sb dot toString. Let's hope this runs. Okay, there is some error. Okay, we have not done this. I hope this works now. And string, oh my god, what am I doing? String builder, new string builder, and there you go, it has been accepted. Let us just submit, and oh my god, this got submitted, accepted. Runtime 1%, 1 ms, and it beats 98% people. So let's analyze the time complexity. It should be n square, right? It is n square. So why is it n square? Because essentially we are going through each numbers again and again, n square times, right? So now this n square is much less than n square, is much less than n factorial. Let's just assume that this toString kind does not exist. So for this is equal to 10, n is equal to 10. This gives me 100, which is much lesser than what is 10 factorial. This is much lesser than 3628800. There you go, right? So this is our optimal approach, and it was based on a simple observation that this is divided into groups, since we have to keep it into sorted array, and then we do the same thing again and again. We first get the value, fix this, then we repeat the same thing from this by removing this from the pool. That is essentially what we're doing. This is the brute force, and I hope you all understood the problem. Thank you and have a great day.